Hello students, in today's class I'll come to on the topic charge distribution. Basically charge distribution are two types. One type is continuous charge distribution and second type is discrete charge distribution. Continuous charge distribution is divided into three parts. First is linear distribution of charge, second is surface distribution of charge, and third is volume distribution of charge. First of all, we have to discuss linear distribution of charge. In linear distribution of charge, charge is distributed along their length, or in other words we can say charge distributed is only one dimensional. Suppose this is a segment of fiber and charge distributed on the fiber is in this manner. Let the length of the fiber is L and total charge on the fiber is Q. That's why total charge on the fiber is Q and length of the fiber is L. That's why charge per unit length is known as linear charge density, which is denoted by lambda, and the unit of the lambda is coulomb meter inverse. Similarly, surface charge distribution can be represented by, suppose this is a sheet of paper and the charge on the sheet is Q and area of the sheet is A. So total charge on the sheet is Q and area of the sheet is A. This is called surface charge density, and unit of the surface charge density is coulomb meter square, inverse meter square. 3. Volumetric charge distribution. Suppose it is a cube which is divided into, it is a cube, it is a three-dimensional structure, and charge on distributed of the cube is total charge is Q and volume of the cube is V. Then Q upon V is equals to volumetric distribution of charge or volumetric charge density, and the unit of volumetric charge density is coulomb meter cube. And suppose the small segment of the wire is dq and the length of the small segment is also dl. So this can be, if the charge distribution is uniform, so this can be represented by dq by dl is equals to lambda. Now we can say for uniform distribution of charge, lambda is equals to dq by dl, or it is also equals to q by l. Similarly, small segment of this sheet is dA and charge on the sheet is dq, and this is also represented by dq by dA is equals to sigma. So it is also represented by sigma is equals to dq by dA or q by a. And just like this, small segment of volumetric distribution, charge on this small segment is dq and volume of this is dv, so it is represented by dq by dv is equals to rho. And for uniform distribution, it represented by dq by dv or q by v. Okay, this is the mathematical expression of distribution of charge. I repeat, first is the linear distribution of charge, second is the surface distribution of charge, and third is volumetric distribution of charge. Now we have to discuss in the mathematical form in detailed form. First case, linear distribution of charge. Suppose this is a segment of wire and the charge on the small segment is dq and length of the small segment is dl, and it is a test charge. The magnitude of test charge is q naught. The position vector of this is r and position vector of this is r naught. Force applied by this segment of charge on the test charge is this, and direction of the force is this, it is df. So df can be written as k q naught dq r cap upon r naught minus r. In previous class I taught you r square. This is the vector form, or in another form df is q naught dq r naught cap upon r square 4 pi L epsilon naught, because the value of k equals to 1 upon 4 pi L epsilon naught. This is for linear distribution. Okay, and similarly this is for volumetric distribution we can write. Okay, now in the another form, if this expression can be converted into q naught, and the value of dq here is dq can be written as lambda into dl. So we put the value of dq this in this expression, we can write lambda into dl r cap upon 4 pi L epsilon naught r naught square. This can be written as in the format of r naught minus r vector mod square, r naught minus r vector mod square, r naught minus r vector mod square. Okay, this is for linear distribution of charge. And now in the second case, surface distribution of charge 2. So we can change here charge on the sheet. Total charge on the sheet is q and area of A, and suppose this is a small segment which has dq charge and area of the segment is dA. Okay, so this can be written as A sigma meter square dA sigma equals to dq by dA, q by A, and this is equals to sigma into dA, small charge. Okay, now the next case we have to change the figure. And the small segment is this. The force exerted by this segment, charge on the segment is dq and area of the segment is dA, and the position vector is r. Okay, next, so df equals to, the first expression can be written in this form, r naught minus r vector. Okay, second step is also just like this, but in third step we have to put value of dq is this. So we can write here sigma into dA. This is for surface distribution of charge. And now third case is volumetric distribution or volume distribution is represented by that type of figure. charge on the whole body is, and the small segment of the cube is this, and charge on the small segment is dq, and the volume of dv. So volumetric distribution of charge, volumetric density, volume density is represented by rho, and here we can replace by the value of A by V, and unit is meter cube. So this term is dV rho equals to dV, and here is V. So dQ equals to V into dV. Sorry, V into rho into dV. Okay, and the diagram can change by the form of this, and the charge on the segment is dq and volume is dv. So the expression can change. First expression just like this, second is similar, and third expression, in third expression we have to put value of dq. This value is put in this case. So dq equals to rho into dv. This is the volume distribution of charge. And now fourth is a discrete form. In previous class I taught superposition principle. The total expression of superposition principle can put here as a discrete distribution of charge. Then the total distribution can be represented by F net distribution, can be represented by F net is equals to F discrete plus F linear plus F surface plus F volumetric. These are force vector quantity, that's why we put here the vector term. So F discrete in previous class, recall your previous class, F net is equals to, this can be written as summation of Q naught and charge is Q, I integer, upon 4 pi epsilon naught R naught minus R integer square moles, and here is R naught minus R integer cap. This is the discrete form. Summation where I equals to 1 to I equals to n. This is the discrete manner. And for linear distribution, Q naught upon 4 pi epsilon naught, and here is lambda dl R naught minus R unit vector upon R naught minus R, okay, plus surface distribution of charge. For the surface distribution of charge, sigma dA R naught minus R upon 4 pi epsilon naught R naught minus R square, and plus volume distribution, we can write Q naught rho dV R naught R upon 4 pi epsilon naught R naught minus R square. And the total sum we can also write in this form, F net is equals to Q naught upon 4 pi epsilon naught is common, bracket integration summation of I equals to 1 to I equals to n Q integer R naught minus Ri cap upon R naught minus Ri square plus lambda dl R naught minus R cap upon R naught minus R square plus sigma dA r naught minus r cap upon r naught minus r square and plus rho dV r naught minus r cap upon r naught minus r square. This is the net distribution of charge. This segment represents to discrete manner, and this is for linear surface, and this term represent to the volume distribution. These three term is called continuous distribution of charge, and this is called for discrete distribution of charge. In the today's topic, we have to we discuss to the distribution of charge for uniform distribution. Means overall of the charge distribution is uniform. This expression is applicable for only these three terms is applicable only for the uniform distribution, and this is for non-uniform. The overall distribution of charge can be represented by these steps. For today's class, this is over, and now in next class we discuss new topic is electric field. Thank you very much.